When sizing a motor cable, determining where to calculate the short-circuit current is crucial. The calculation should be performed at the motor's connection point. This location represents the point of highest current demand, consequently experiencing the maximum short-circuit current flow. While the National Electrical Code, or NEC, doesn't explicitly mandate cable sizing based on short-circuit level, Article 110.10 emphasizes the necessity of protecting equipment from overcurrent hazards. This necessitates selecting a cable capable of withstanding the maximum prospective short-circuit current without overheating or posing a fire risk. The three primary methods for determining appropriate cable size are firstly, current capacity. This method focuses on determining the maximum current a cable can continuously carry without exceeding its temperature rating. The ampacity of the cable must be equal to or greater than the motor's full load current, accounting for any dirting factors due to ambient temperature, conduit fill, or other conditions. Secondly, voltage drop. This method involves calculating the voltage reduction along the cable length when carrying a specified current. Excessive voltage drop can impair motor performance, causing reduced torque and potential overheating. The NEC recommends limiting voltage drop to no more than 5% from the source to the motor. Thirdly, short-circuit level. This method focuses on determining the cable's ability to withstand the high currents associated with short-circuit faults. The cable must be able to withstand the let-through energy, expressed as I²T, of the protective device during a fault condition. The cable size should be determined by the largest of the three values calculated using these methods, ensuring adequate ampacity, acceptable voltage drop, and sufficient short-circuit withstand capability. To elaborate on current capacity, the ampacity of a conductor is its current carrying capacity in amps. The NEC provides ampacity tables, such as Table 310.16 for conductors in raceways or cables, and Table 310.17 for conductors in free air. These tables list ampacities based on conductor size, insulation type, and ambient temperature. For example, a number 4 American wire gauge, or OG, copper conductor with THHN insulation has a higher ampacity than the same size conductor with TW insulation. These ampacity values are based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature exceeds this value, a correction factor must be applied to reduce the allowable ampacity. These correction factors are found in NEC Table 310.15b. Similarly, if multiple current-carrying conductors are installed in the same raceway or cable, a directing factor must be applied to account for the increased heat generated. These adjustment factors are listed in NEC Table 310.15 . Voltage drop calculations involve determining the reduction in voltage from the source to the load due to the cable's impedance. The voltage drop is directly proportional to the cable's length, the current flowing through it, and its impedance per unit length. The formula for calculating voltage drop is volts drop equals 2 times K times Q times I times D divided by circular miles, where volts drop is the voltage drop in volts, K is the direct current resistance for the conductor material, which is 12.9 ohms for copper and 21.2 ohms for aluminum, Q is 1 for direct current or single phase and 0.866 for three-phase circuits, I is the current in amps, D is the one-way distance in feet, and circular mils is the area of the conductor in circular mils. To determine the appropriate cable size for voltage drop, first calculate the allowable voltage drop based on the NEC recommendation of 5%. Then, using the voltage drop formula, solve for the required circular mils. Finally, select a cable size from the NEC tables that meets or exceeds the required circular mils. For example, if the calculated circular mils is 26,240, a number 6 AWG conductor with a circular mil area of 26,240 circular mils would be sufficient. Regarding short-circuit level calculations, the cable must be able to withstand the thermal stress imposed by the short-circuit current. The amount of energy a cable can withstand is determined by its I²T rating, where I is the short-circuit current in amps and T is the duration of the fault in seconds. The I2T rating is a measure of the amount of heat the cable can absorb before its insulation degrades and fails. To calculate the required cable size for short circuit withstand, first determine the available short circuit current at the motor terminals. This can be calculated using the utility's available fault current and the impedance of the transformer and conductors. Then, determine the clearing time of the overcurrent protective device, such as a circuit breaker or fuse. This information can be obtained from the manufacturer's datasheets. Next, calculate the I2T value using the formula I2T, where I is the short circuit current and T is the clearing time. Finally, select a cable size that has an I2T rating greater than or equal to the calculated value. Cable manufacturers provide I2T ratings for their cables. For example, a number 4 AWG THHN copper conductor may have an I2T rating of 50,000 amps². If the calculated I2T value is 40,000 amps², then the number 4 AWG conductor would be sufficient. In summary, calculating the short circuit level at the motor's connection point is essential. It's also essential to consider current capacity, voltage drop, and short circuit level to select the right cable size. This ensures safe and reliable motor operation and adheres to NEC guidelines. By calculating the maximum current the cable can carry, calculating the voltage drop in the cable, and calculating the maximum short circuit current, the largest of the three values is used to choose the appropriate cable size.